This is the chemical changes topic in AQA GCSE chemistry. It's a dual award and a triple award topic, so all students would benefit from working through what's on this video. Chemical changes is incorporating exo and endothermic reactions, and that's where we're going to begin. I'm going to recommend you try the activities pausing as you go. So we need to know about the principle of conservation of energy. That's the fact that energy is neither created nor destroyed, merely changed from one form to another. And we need to know what observations we would make in exo and endothermic reactions and why that is the case. Now we're going to do this by looking at a couple of practicals. If we take two different reactants and measure them, combine them in a calorimeter and measure the temperature change, we're going to see what would happen. And these are the examples that we're talking about. So copper sulfate with iron filings, hydrochloric acid with magnesium ribbon. We've got anhydrous sodium hydrogen carbonate with ethanoic acid. We have hydrochloric acid with sodium hydroxide, and we have water with ammonium nitrate. And I'm actually going to provide you with some data here to help you answer some questions that follow. We're going to take the initial temperature as 20, which is potentially the temperature in the room where these took place. And as we did them and we reacted them and we stirred them with a thermometer, we would see potentially the following temperature changes. First one up to 28, second up to 31, third down to 16, fourth up to 23, and the fifth down to 12. So there's three of them where the temperatures have gone up. And we can see those here. I've put those in red to indicate higher temperature. And there are two of them where the temperature has actually gone down. And we can see those here. So now let's have a think, based on the information in this blue box, about which of those are exo and which are endothermic reactions. So in an exothermic reaction, heat energy is released to the surroundings. In an endothermic, the reverse is true. The energy is taken in from the surroundings. So what do we think for exo and endothermic? In an exothermic reaction where heat energy is released to the surroundings, the temperature of those surroundings goes up. Now, in this particular reaction, that means the surroundings within the calorimeter, the solutions that have been mixed. In the endothermic reaction, the temperature of the surroundings goes down. So let's take a look at them on here again. And we've got 1, 2, 3 exothermic reactions because the heat energy has been released, causing the temperature to go up. And we've got 1, 2 endothermic reactions where the temperature has gone down. There's also a required practical within this topic. There's a big apparatus list there, and we've got a diagram so we can see what is going to take place. So we're doing this within a polystyrene cup, reacting two different reagents and measuring the temperature change. The method in a little bit more detail, we're doing sodium hydroxide and we're adding hydrochloric acid. So we're doing this in a polystyrene cup, but that is supported in a beaker. That's because the polystyrene cup could lose its balance. The beaker gives it that stability. We're then going to take our 25 cm cubed of sodium hydroxide, add 25 centimetre cubed of hydrochloric acid, but we're first going to take the temperature for 2 minutes, every 30 seconds for 2 minutes before the reaction takes place. At 2 minutes, we add the HCl, we stir, and then we begin taking the temperature again. Now that can then be repeated, a second experiment doing copper sulfate with iron filings, and finally potassium hydroxide and nitric acid. So let's have a think about what the results table would look like if you needed to draw one from scratch. With any table that you are asked to design, we're really looking for one thing. We're looking for the fact that you've got columns for the independent and the dependent variable, and then we want you to show that you have given units in both of them. So that might look a little bit like this. We might have the time and the temperature, and we've got time and temperature again over here, and then not forgetting the units, time is in seconds and temperature is in degrees C. And then you simply put the data in. Now time, it says every 30 seconds, so do that in seconds. 0, 30, 60, 90. At 120, remember, you're adding the reagents, so you wouldn't take a temperature there. And that would actually go all the way through to 600. Now let's think about the sort of questions that a practical like this might bring. It's about understanding the chemistry, but it's also about remembering the methodology. It's remembering what you're doing and why you're doing it. So, question 1, we're looking at the reaction between hydrochloric acid and sodium hydroxide. We know that an acid and an alkali make salt and water. What would the symbol equation look like for this reaction? Well, you've got to know that hydrochloric acid is HCl and sodium hydroxide is NaOH. You've also got to know that hydrochloric acid makes chlorides, that it's going to be sodium chloride because the sodium from the hydroxide moves in, and then you need to know the formula is NaCl. And sodium is in group 1, chlorine is in group 7, so a +1 ion, -1 ion, we've got our formula. And we remember we're making water and we know the formula for that. We need the state symbols. Now, each of these three are ionic and they're being done in solution, so they're all aqueous. But water, we must remember, is never aqueous. We're going to put that as a liquid. Aqueous means dissolved in water. Water is not dissolved in water. So what about if you're asked for the Ionic equation? Well, this has come up in the previous 2 chapters as well, but it is a really important skill to have. The first thing that you do is you break down everything that's ionic and aqueous into its ions. So here we go. HCl becomes H plus and Cl minus. Sodium hydroxide, Na plus and OH minus. Sodium chloride, Na plus and Cl minus. The H2O is covalent, so we don't break it down at all. What we then need to do is get rid of the spectators. We need to get rid of things that exist on both sides of the equation with no change to them. They don't have a part to play in the equation. So Cl minus stays as Cl minus, so let's get rid of that. Na plus stays as Na plus, so let's get rid of that. And we're left with the overall ionic equation, which is what's left. H plus OH minus goes to H2O. And that is the ionic equation you will get every single time you do an acid-alkali neutralization. Now, do we think it's an endo or an exothermic reaction? You've obviously not done the reaction here or the practical, but you will potentially have done it in the past, and the temperature does go up when the reaction takes place. For that reason, we can be confident that it's exothermic. Exothermic because the temperature of the surroundings increases. In this case, that's the temperature of the solution that we've made, of the salt solution when the acid and the alkali mix. Heat is lost to the surroundings from the reagents. Now, we're going to talk about heat loss in a slightly different way later on. Now let's consider the second pair of reagents, copper sulfate and iron, and we're reacting those. So what would the equation look like here? Well, again, you've got to know that copper sulfate is CuSO4 and iron is Fe, so that's from the periodic table, and we need the state symbols again. Now, hopefully what you're recognizing here is that this is a displacement reaction, a more reactive metal displacing or kicking out a less reactive metal. So displacement reaction means we would end up with solid copper and iron sulfate aqueous. So again, what would an ionic equation look like for this reaction? Well, let's break down the ionic aqueous substances. My copper sulfate becomes Cu plus 2 and SO42 minus. My iron sulfate becomes Fe plus 2 and SO42 minus. I'm not changing my Fe or my Cu. They're solid and they're metallic. I can now get rid of spectators. I've got SO42 minus on both sides of this equation, so I can disregard them, and that then allows me to write the full ionic equation, which we can see here. Is this an exothermic or an endothermic reaction? Well, again, I will tell you that the temperature goes up, and that means it's exothermic. The temperature of the surroundings goes up. The heat is lost to the surroundings from the reagents. Again, we're going to talk about heat loss in a slightly different way when we talk about improvements to these practicals later on. So then we've got our third chemical reaction taking place. It's an acid-alkali again. And in this case, we've got HNO3, nitric acid. Yes, you need to remember it. Potassium hydroxide, KOH. You would need to know that. Making potassium nitrate, KNO3 and H2O. A familiarity with these formulae is going to be very, very important. I've got my state symbols again. Aqueous, aqueous, aqueous. And the water is liquid. Now let's do the Ionic equation. Break down everything that's ionic and aqueous into its ions. And we see that here. H plus, NO3 minus from the HNO3, etc. Get rid of spectators. I've got NO3 minus on both sides of this equation. I've also got K plus on both sides of the equation. And we've already established earlier in this video that for any neutralization reaction, acid-alkali, this is what we're going to end up with. H plus OH minus goes to H2O. Was it an exothermic or an endothermic reaction? Well, it's exactly the same as the others. Temperature goes up, which makes it exothermic. Heat is being lost as the reagents react. Temperature of the surroundings, the solution, goes up, so we measure that temperature increase. So when we're talking about measuring temperature, why is a polystyrene cup better to use than a glass beaker? Remember, we used a glass beaker to support the polystyrene cup. But the polystyrene cup has an integral role within this. And the reason is that polystyrene is a better insulator. It prevents heat loss to the wider surroundings. Because if I'm measuring the temperature of the solution where the reaction is taking place, if that heat is being lost to the air that surrounds it, we're not going to get a reliable temperature measurement. So we use polystyrene for that reason. Why did we not take the temperature at 2 minutes? You may remember in the table, we left a blank there. And that's because that's where the reactants were added. We had taken the temperature for the first minute and a half, and that's to let us see if there's any changes to temperature within the room, if there's an upward trend, a downward trend, or more likely that it's staying consistent. And that means that we can be confident that that's our starting temperature that we can measure the change from. Now, finally, a key improvement with this, and let's take us back to the diagram so we can see if there's anything that we could change. And remember, we're speaking potentially about preventing heat loss. The polystyrene cup goes a long way, but what else could we do? The key thing that we're looking for here, we could put a lid on the polystyrene cup. That will prevent further heat loss to the wider surroundings, and it will mean that we will get a far more reliable temperature reading, maximum temperature for the chemical reaction that we have taken place. Now, that would also be true if this was an endothermic reaction. We could have done this. We've done 3 exothermic reactions. We could have done them where the temperature had gone down, but we would follow exactly the same procedure. That takes us to the end of this video. Thank you for listening, and goodbye.